Hello and welcome. This video is going to cover the basic tools of geometry, and here are the bulleted portions of what will be covered, and there will be a whole lot of example problems as well. So if you know enough about algebra, this is kind of the kickoff point for everything geometry related. Now, geometry also is focused on circles and triangles and such, and we'll get to those over time. But here, we're going to look at points, lines, and planes, segments, rays, parallel lines with planes, measuring segments and angles, basic constructions, meaning using a compass, and the coordinate plane. And the example problems on here, they have numbers. I'm using them for a class, so please ignore where I skip some numbers here and there. They'll go in sequence and then they'll jump around a little bit. Alright, so here's a vocabulary word bank. Here are all the kind of the terms that you would want to know based on these concepts that we were talking about. From this word bank, I'm going to choose some of those words to answer and fill in some of these blanks right here. So let's choose the correct term to complete each sentence. Figures that are in the same plane are coplanar. Okay, means I can get a whole bunch of points like A, B, C, D, E. Let's pretend that this plane right here that I'm talking about is your computer screen, your monitor, and I'll just draw a rectangle to represent that. This is your computer monitor. All 5 of these points are coplanar because they are all flush on your screen. Pretend like there are other planes that can come in and out of your screen as well. But those 5 points were on it. Okay, let's find the part of a line consisting of 2 endpoints and all points between them. That would be a segment. Okay, so all points between them, really think about the fact that a line really is just a series of a whole bunch of points. I mean, if I go here, blah, 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 blah. All those points make up the line. So it says all points between them, that's what we're talking about. A line goes infinitely in both directions, extends infinitely, and a ray extends infinitely in one direction with one endpoint. A segment has 2 endpoints. 2 segments with the same length are congruent. Congruent meaning equal in size and shape. I don't actually, congruent segments. They are congruent segments. I'll write that. So they are equal in size and shape. The blank of a segment is a point that divides the segment into 2 congruent segments. That is called a midpoint. I see why you might be thinking bisector or something like that. We might even see that later. However, we're not talking about something that goes through the segment itself. We're talking about a portion of the segment. That portion happens to be the very middle of it. Okay, a blank is a ray that divides an angle into 2 congruent angles. So this one's actually a ray. This one is a bisector of angular proportions. An angle bisector. Okay, a blank is an accepted statement of fact. That would either be an axiom or a postulate. Either word works. In fact, I don't actually know the difference between the 2 words. I think they're literally just synonyms, and there's nothing else you can really say about them. Blanks are coplanar lines that do not intersect. So what kinds of lines would not intersect if they were on the same plane? Those would be called parallel lines. And finally, a blank or en blank is an angle whose measure is between 90 and 180. That would be an obtuse angle. Okay. So obviously I didn't use every word in this word bank. I want you to see the other ones, but these are examples of what these ones mean or how they can be used. Now I might use any one of these as I continue on with this. Okay, let's start and do some example problems. I'm going to have some stuff up here that might help you understand the rest of the way. So points that lie on the same line are collinear points lying on the same line. Points and lines in the same plane are coplanar. Segments and rays are parts of lines. Remember, line is the entire thing. A segment is a small portion of it. A ray is a larger portion of it where it extends one way. Lines that are coplanar and do not intersect are parallel lines. We just talked about that. Lines in space that are not parallel and do not intersect are skew. So we're going to look at some of those. Planes that do not intersect are parallel planes. Okay, so let's look at numbers 19 through 22 and look at the figure for the right for that. Let's name two intersecting lines. Doesn't matter which two. So all we need to do is take one line. I'll just take this one back here, line TS. And by line, I really should indicate with arrows here that it goes forever. Now, any other line that intersects with TS would be, at least as far as the ones that make up this actual box, SR, SC, QT, TD, ta-da. That's kind of it. You could draw more. I could draw one from A to T, or B to T, or R to T, or Q to S, or whatever. Notice what is the same for all of these is if I'm taking one line, the ones that need to intersect have to also have those points on it. So it's easy when I name this, like line QT intersects with line TS. Why? Because they both have point T on it. That's that. Okay, name three non-collinear points. So non-collinear, any three here will be non-collinear because there are only this many sets of points. Like for instance, if I had another point right here called point F, and I could draw a line through Q, T, and F, then those would be collinear. But there aren't any 3 points that are in a line here. So name any 3 points. Q, T, and D. Right? QT has a line here, T and D has a line here, Q and D has a line here, but they aren't all the same line. So Q, T, and D. You can name any 3. I'm just giving you an example. Name a pair of parallel planes, so planes that do not intersect each other. If you think of this as a room, right, with 4 walls, a ceiling, and floor, and you're looking inside of it, then think about which planes never intersect. Now remember, planes go on forever, so this plane, QABR, goes forever up, down, right, and left, and it's closer to you than plane TDCS. But planes QABR and TDCS are parallel. Think of the front of the room that you're sitting in and the back of the room that you're sitting in. And if those are parallel, if they extended forever, they would never intersect with each other. They always stay the same width apart. So a pair of parallel planes here that I'll name are those quote-unquote front and back planes. Plane QABR, or I'll just say QAB, and TDC. Remember, you can name planes with just 3 letters because this QAB identifies the front, TDC identifies the back. Name 3 lines that intersect at D. So as we said before, you just need lines that actually go through that point. So here's a line DC, here's a line AD, and here's a line TD. Now I could do more. Take a look at this. You really want to get a good perception of this. I could draw one from R down to D, and it's going through. Now what is it doing? Think about your room. Once again, here's a bottom corner of your room. Here's a top corner of your room on the other side, right? You can draw a line through there. Just because it's not being represented by the planes from this box doesn't mean you can't draw a line from R to D. But those were 3 that I talk about as well. Now, how are they written? They need lines above. So AD, TD, and what I say, CD. So there you go. Okay, complete these statements with always, sometimes, or never to make a true statement. A line and a point are blank coplanar. Well, the answer is always, and I'll try and do the best I can to help you out with why this is. I'm just going to first by stating this axiom. Now make sure you listen to this. Any 2 intersecting lines are always coplanar. Okay, any 2 intersecting lines are always coplanar. So pretend like you had 2 lines out in space. I'll just draw 2 right here. Here's one. Here's another, right? These 2 lines intersect. So the plane that they're on, that they happen to be on in this case, are on your computer screen, right? Now lines are an infinite series of points. Now hear this axiom. Between any 2 points, you can draw a straight line through them. So what if I took this concept, these 2 lines are on my computer screen plane. What if I drew a line through one of my points here? If here's another point, it doesn't matter what plane it's on, but this one's on your computer screen. If there's another point that's on here, couldn't I draw a line from this point to that point that has a line on it already? Yes. So anytime that you have one line somewhere in space, you pick another point out in space, you can always draw a line from that point to the line and intersect that. And because that postulate's true, then this statement has to be true as well. These always should be able to have a plane on them. Okay, number 24, two segments are blank coplanar. Well, here's the thing with all these statements. I want you to try to make the case that they're always coplanar. Okay? By that I mean give examples where they work and prove that examples don't work as well. So here's a segment and here's a segment. So QR with RS. I can do those two segments right there, and I can say that they're on the same plane, QRS. I could even do it with QA, and I could say these two are on the same plane, QAB, this one right here. So I know that it might be sometimes true. Let's see if it's always true. Someone else might say, oh, no, look at this one, DC. And then you're like, well, no, you know what? You can draw a plane through that, QDCR, right? So wait till someone can prove you wrong. You're like, AB. No, BC. They got you. There's a plane that's not on the same plane as QR, right? So there's an example by showing that it can sometimes work and sometimes not work. Sometimes they are not coplanar. So there's just but one example. So with these next two, I'm going to go with that always, sometimes never thing by thinking always first and see if it ever works. Skew lines are always coplanar. Let's say it was always. Then you have to tell us at least one example where it works. Okay, QR and a skew line would be DA, right? They are, no, skew. If you keep working, you'll figure out they never intersect and they're not parallel. Therefore, they are not on the same plane. Therefore, they are never coplanar. Number 26. 2 points are blank collinear. Well, we just talked about that one. That one's also an axiom or postulate. This one's always true. Okay, next screen. Segments with the same length are congruent segments. We talked about that. A midpoint of a segment divides the segment into two congruent segments. We also talked about that. Two rays with the same endpoint form an angle. Okay. Angles can be classified as acute, right, obtuse, or straight. Now, acute is less than 90. Right is 90. Obtuse is between 90 and 180. And straight is 180. I should say that acute is between 0 and 90, actually. Angles with the same measure are congruent angles. So let's number 27. Find two possible coordinates of Q so that PQ equals 5. So Q would be a new point that you would establish on here. And the whole point here is that this is a one-dimensional number line where points can go in either two directions, negatively and positively. Point P is on -2. So point Q would have to be 5 away from there to the right or to the left. So Q could either go to 1, 2, 3, 4, 5, same as where H is. Okay, so Q could either equal 3. Or to the left, 1, 2, 3, 4, 5 would be at -7. So you subtract 5 from -2 and you add 5 from -2, you'll get your two values of Q at 3 and -7. Okay, number 28, find the coordinate of the midpoint of PH. So the midpoint, again, is something that divides these segments congruently into two. So what you could do is you could literally count. You could say, what point is exactly in between these? Well, one way to really do it is to say how far apart they are, which they're 5 apart because that's the length of PH. And you have to take half of it to see how far over you should go. So 5 over 2 is also 2.5. 2.5. So if I go 2.5 over in either direction, in the right of P or the left of H, you'll find this point right here that ends up being the midpoint, and that is 0.5. Okay. Another way of doing that, of taking that average, if you don't have the visual, is you literally do take the average. The midpoint is adding your two values and then dividing by 2. Dividing by the number of values that you're adding together. So -2 plus 3 is 1, and 1 over 2 is 0.5. So that also gets you your location. Okay, find the value of each variable. We're looking at numbers 29 and 30. Okay, 29, what we have here are 3 points. These tick marks indicate that these 2 points are congruent, which must mean that this is the midpoint. Either way, what we're going to do is set up an equation where this expression is equal to this expression. So let me just write that right now. 3m plus 5 equals 4m minus 10. If I subtract 3m from both sides here, on the right side I'm going to get m. If I add 10 to both sides here, on this side I'm going to get 15. So there you go, m is 15. And if you wanted to find these actual lengths, substitute 15 for m, and you should get the same number either way. It looks like it'll be 50. 15, 50. Okay, number 30, there's no indication that these, now these are angles, these aren't lengths, but there's no indication that these are congruent. However, if there's something that you know about a straight angle right here, is that they're 180 degrees. And if you separate it with a ray, well, when we add this angle with that angle, we should get 180 degrees. These are called supplementary angles. So if I add 3x plus 31 with 2x minus 6, I should get 180. Now I got to combine like terms. We get 5x plus 25 equals 180. Subtract 25, you get 5x equals 155. Divide by 5, you get x equals 31. So 31 isn't a number of degrees. It's a number that you substitute into here so you can get these angles. And it looks like this one would be, I think, 331. 93 plus 31, 124 degrees here. And this would be, well, you could either substitute here and I think get 56, or you could have subtracted 124 from 180 and you'd also get 56. These should add up to 180, and they do. Number 31, name a pair of each of the following. Okay, so using this diagram here, let's name some pairs of complementary angles, supplementary angles, and vertical angles. Okay, complementary angles are angles that add to 90 degrees. Supplementary angles are angles that add to 180 degrees, as we just talked about. And vertical angles, they're congruent, but it's not just all different congruent angles. It's angles that face opposite each other. From two opposite rays. I'll make sure to look at those in a second. Let's go with complementary angles first. What we need to do is recognize any 90-degree angle, potentially. So this one's 90 degrees with the marking. Now, if this is 90 degrees, so is this one here, so is this one here, and so is this one here, by the way. However, these other ones, angles ADE, EDF, and FDC, do not have a ray drawn through them so that you can get two angles that add to 90. Only this one really does that here. So I have angles ADB, and angle BDC, and those two are complementary. Those two add to 90 degrees. Now, they don't have to be right next to each other, forming an exact right angle to be complementary. If I had another one that was right here somewhere, and somehow this one plus this one was 90, then these two would be complementary as well. However, we don't have that scenario, and I really only need one, just one pair. Okay, B, let's take a look at supplementary angles. Just as I was talking about before, they don't need to be right next to each other to add 180, but it might be the best way to do it. So I could look at any of these, like say this one and this one. Now they're both right angles. They're both congruent, but they also both add to 180. So that's angles CDF and FDE. Those are supplementary. Let's get a pair that where neither are 90 though. Because this ray draws through some of these, let's take a look at this one. Angle CDB, and boom, right there. Angle BDE. Those two add to 180 as well. Okay. One last example I want to give you are two that aren't necessarily adjacent to each other, meaning they're not neighboring each other perfectly. So we could look at CDF and ADE. Those are both 90-degree angles that add to 180. So those are supplementary. Okay, they don't have to be adjacent to each other to be supplementary. Okay, vertical angles. So the one I just drew, actually, I just erased it. Let me bring it back. This is an example of vertical angles. They're angles that face opposite each other. Notice that this one faces this way, this one faces this way. And they're formed, the angles are formed by pairs from this should say two pairs of opposite rays. Two pairs of opposite rays. So here's a set of opposite rays, DF and DA, and then DE and DC are also opposite rays. Basically, straight lines that intersect form possible vertical angles, such as this one right here. This is also for C, CDF and ADE. And there's also this pair right here that go up and down. Now these are also 90 degrees. Remember, all vertical angles are congruent. They're not always 90 degrees, but this is angles EDF and ADC. Okay, there's your vertical angles. Okay, whip out your protractor, your compass, and your ruler. Let's do some of these things based on here. Now, construction is the process of making geometric figures using a compass and a straight edge. 4 basic constructions involve constructing congruent segments, congruent angles, and bisectors of segments and angles. Here we're going to do perpendicular bisectors, which is next. Perpendicular lines intersect at right angles, so over here we had sets of perpendicular lines down on the bottom. Okay, a perpendicular bisector of a segment is perpendicular to the segment at its midpoint, so therefore it bisects it into 2 congruent segments. You can only bisect segments. You can't bisect lines or rays because those don't end. An angle bisector is a ray that divides an angle into 2 congruent angles, so we talked about that on the first slide. Okay, so first we're going to use a protractor to draw a 64-degree angle, then we'll construct an angle congruent to it by using the compass. So what I'm first going to do is go to my protractor here. I'll go and set my measure at 64 degrees. So here's 0, goes all the way up. We're going to get about up there. And I'm going to ditch the protractor once I get my measure here. So I think that's about 64. Okay. I'm going to get rid of this protractor. I don't think I need it again. So I have this angle. What I want to now do is use my compass and make a congruent one right here. So using any width, hopefully long enough that you can do something with it, like this one. I'm going to go ahead and draw an arc on this. Okay. I'm now going to create a new segment over here, and I'm going to draw that same arc. Okay, so putting my pivot here on that vertex, I want to go ahead and draw a new one with the same width. Basically, I'm going to create the same reference intersecting points. Now what I want to do is go back to my original angle, go to one of my 2 intersecting points with arc and side, angle side, and I'm going to try and match the width here of the compass with, well, I can't do it perfectly, you see, but I can try and match the width of the compass here with the with these 2 points right here. And then if I signify what I'm talking about there, I can draw an arc, and as I go over here, keeping that same width, I just need to draw another arc here as well. When I do that, I will have created essentially a point of intersection that I want to draw a segment through. So my third action here is starting at this vertex. I would use a straight edge if I had a piece of paper, but I have a line tool, and I'm going to draw that point of intersection going through right there. And voila, I've created, as best as I could, a angle that is congruent to this other angle. Okay, so let's see, was I close? Pretty close. So that was all with the compass and protractor. 33, use a ruler and draw a PQ so that it's 3 centimeters long. So I have my ruler here. Let's draw a segment 3 centimeters long and call it PQ. Okay, don't need the ruler anymore. Okay, now let's use the compass and construct congruent segment AB, something that's congruent to PQ here. So taking the compass, what we're going to do on this one is bring it back up. Let's create a width that is equal in measure to my segment. So rotating back, getting it flush, widening it out. It's about as best as I can get, about right there. I'm sorry, this won't be perfect, but whenever it's 3 centimeters long, I guess that's the best I could do. So, okay, about that length. See how there's going to be a little bit of cutout, or it's a little bit farther, so maybe I'm going to try the same thing over here. So what I'm going to do here is make a new point, and I'd like to place my pivot on that point, and going back, I'm going to draw another arc right here. What I'm going to do from there is draw a segment outward from point to arc, and maybe just a little bit past it, like last time. And these end up being congruent segments. Okay, so these two are plenty congruent. Okay, next part, construct the perpendicular bisector of AB. Okay, so in order to do this, what I need to do is take my compass, place the pivot on one end point. I'm going to shrink this, so I want it to be past the midpoint, so as you can tell where the midpoint actually is, it's right there. I want to make sure it's a little past it. Do your best guess, but you know that this isn't past it. Don't get too close, now you're not certain. Get past it. Draw an arc up and down. We're going to do it high and low enough so that we know it's passing the midpoint above and below it, like so. Now what I'm going to do is reverse my compass, place it on the other endpoint right there with the same width. Okay, and then I'm going to construct another arc just like that, so I get 2 points of intersection. Doing so, I will now take, I would take my straight edge, I don't have one, but I take my straight edge or my line tool, and I'm going to draw a line that goes through, I'll do a little better than that, line that goes right through those 2 points. I think that'll be fair. And voila, what you have done is constructed not only a segment line array that goes right through its midpoint, if you take a look at using the line tool, going right through the midpoint, but I've also made something that's 90 degrees. So this becomes a perpendicular bisector to AB. If I called it CD, then I'd say that CD, let's call this point E. CD is, let's say it's a segment, is perpendicular to AB, segment AB, and segments AE and BE are congruent, or EB. There we go. Okay, midpoint and distance formula. Here are 2 new terms and formulas for them. The x-axis and y-axis intersect at the origin 0, 0 and determine a coordinate plane. You can find coordinates of the midpoint, denoted M, capital M, of AB, of if point A was x1, y1, was at x1, y1, point B was at x2, y2, we can use what's called the midpoint formula. Basically, it's like when I found the midpoint before, right here, I either counted the distance, found half of it, and then found the point that's exactly halfway in between, or the location of halfway in between right here is taking the average of your 2 points and then dividing it by how many points there are, 2. And that'll be the actual location. But here, you need an x term and a y term for midpoint. Okay, and then the next one, you can find the distance d between points A and B at x1, y2, x2, y2 using the distance formula. Now, this distance formula is not much different from Pythagorean theorem. In fact, I want you to think of them as the same thing. This one's a little more complex looking. It has subscripts and a lot more terms than this one. If you consider any of these points to be right triangles, find the distance between where their legs would be if they draw horizontally and vertically, and then you can use Pythagorean theorem from there. So I'll look at both ways using these examples here as I find the distance first. Rounded to the nearest tenth. Okay, so first one I have -1, 5, and 0, 4 is my 2 points. So I'm going to do this one by drawing it. I want you to understand this one before we use the formula. So here's a point 1, 5. And then another point, 0, 4. Ooh, that's right next to it. So those are really close. Let me redraw that. -1, 5, boom. And then 0, 4 is right here. Okay, what I want you to think about is the fact that there's kind of a right triangle that exists right here. If I draw down to the height of B and across to the width, to the location of B right there, I want to find this distance, but what I've essentially created here was a right triangle. Boom, and I need to know what the distance is in height right here, that's 1, and the distance here in width, that's also 1. Right, distance is always positive. You can consider it to be negative, that's okay. You can subtract these, like here, I would do 5 minus 4 and -1 minus 0. 5 minus 4 is 1. -1 minus 0 is also, oh, well, that one's -1. So like I said, it can be negative because what I'm going to do is square these numbers. A squared plus B squared equals C squared. Let me get that a little thicker. So 1 squared is 1. 1 squared is 1, so C squared is 2. So C is the square root of 2. That number is 1.414, so rounded to the nearest tenth, it's 1.4. Okay, now you might say, you didn't use the distance formula. Well, I kind of did. We squared the difference of two numbers, added together, and took the square root of that. So this time I'll go straight into the distance formula. And the next one I'll try and do all in my head. I want to talk about what those are. All right, this one will be straight up distance formula here. D equals the square root. I can't really do a straight line. Of, let's call this one x2. So 6 minus -1 quantity squared plus, now if this one was x2 and this was x1, then this has to be y2. 2 minus opposite, boom, of 1 squared. So let's see if I can do a straighter one here. Yes, better. All right, 6 minus -1 is 6 plus 1. That's 7. So we got to square 7, and we got to square 2 minus -2 plus 1 is 3. 3 squared. So the square root of 49 plus 9, it's the square root of 58, and that is about 7.6. So that's the distance between those 2 points. Right there, 7.6. That's the length of CD, I should say. Okay, last one, number 36. Now I said I'd try and do this one visually. Again, I want you to get a count. We're trying to find the distance between the 2 points, -7 and 5. The distance between -7 and 5, from -7 to 0 is 7. From 0 to 5 is 5. 7 plus 5 is 12. So one of my numbers in my triangle is 12. I'm going to square that one. It's like the x values. The most visual I'm going to get for you is this length is 12 here. And then here, from 0 to 8, the distance is 8. That's the vertical distance there. So this plus 8 squared, that equals C squared. So there's your setup, right? I didn't have to plug in all this stuff. You still have to calculate it though. So 144 plus 64 is C squared. C squared is 208. And C is the square root of 208. Should be between 14 and 15. It is 14.4. About. These are all approximated. They're rounded to the nearest tenth as they were asked. Okay. Let's do some midpoint problems keeping this formula in mind and the same ideas I was talking about before. There are some ways you could visually make these happen as well. Okay. Find the coordinates of the midpoint of GH. Okay, so if I had, boom, I'm going to make a little graph. If I had these points here, -3, 2, and 3, -2, I want to find the midpoint. So basically, think about the visual representation that I talked about before. What if you had the line, you found the distance between the line in vertical and horizontal sense, you cut it in half, and then you found location that way. So for instance, what I could do is figure out how far down and over this goes. It goes 1, 2, 3, 4 down, and it goes 1, 2, 3, 4, 5, 6 over. So half of 6 is 3, which is 1, 2, 3 over, and half of 4 is 2, 1, 2 up. That is the midpoint, and then you'd have to determine the location, which is 0, 0. Now sometimes the numbers are too big to do this. Sometimes sometimes you don't land on a perfect number, so let's make sure we also utilize the midpoint formula as well. But that's what we did here. We're going to take the sum of our x values, divide them by 2, and the sum of our y values, divide them by 2, and then we'll get the exact location. So here we go. Find the coordinates of the midpoint of GH, so we'll do midpoint as x1 will make -3 plus x2 is 3 divided by 2, comma, y1 will be 2 plus y2 is -2 divided by 2. So -3 plus 3 is 0, and 2 plus -2 is 0. So your midpoint is still 0, 0, as it should be. Okay, second one, find GH to the nearest tenth. I think we mean the distance, so let me take out that segment guy right here. I don't think that should be there. Find GH to the nearest tenth. I kind of have it set up for you here. We found the distance between 2 and -2, which is 4, and -3 and 3, which is 6. So we're going to use Pythagorean theorem, or distance formula, but they're both the same thing. So 4 squared is 16, 6 squared is 36. 16 plus 36 is 52. So the square root of 52, it's close to 7, right? It's close to the square root of 49. That number is 7.2. And that's the distance to the nearest tenth. So there you go. Fiend.